Hello YouTube, going to be showing you some quick tips and a little brief guide on how to use a multimeter to check various electronic components. Very important that if we're trying to find a fault or construct a circuit that we actually know our components are good to start with, or in the case where we're fault finding, help us identify where a component might be faulty. Now when we're doing fault finding, we quite often, if we're working on a circuit, would start at the most logical point. For something that's not working at all that runs on batteries, we'd probably start off by checking the batteries. Just the same as if it was mains, we might check the fuse. I won't show you how to actually remove a fuse from a plug. I'll presume that if you're confident enough to do that, you'll safely remove a fuse from the plug. It's not recommended that you work on mains electricity without proper training. So what we'll do first of all is have a look at a couple of batteries. So here's some batteries, 1, 2, 3, 4. What we'll do is use the multimeter and actually check how good these batteries are. First of all, a little bit about the multimeter. The multimeter is given its name because it is a meter of multiple things. We can check all sorts of things using the multimeter here. This one in particular does voltage in AC and DC range. Generally, if we're testing a battery, it will always be DC because batteries provide DC current. Things like generators and the mains provide AC. We have an MV here for reading some very small voltages. We have the omega sign, which is for measuring resistance, of course. This multimeter has a clever little function where if I press select, it will go into a secondary test range, and the secondary test here is also capacitance, which is a nice little feature. We have a circuit tester here. It makes a beep if the circuit is connected. We'll demonstrate these. We also have a diode test feature. This also has a frequency counter built in, which is quite handy, and that's represented in Hz. We also have a temperature sensor ability here, although I don't have the correct temperature probe for this anymore. We can also measure microamps, milliamps and amps in the 10 amp range. 10 amps being the maximum in here. Quite often these will have they should have a fuse in them, and if you've actually overloaded it with more than 10 amps you can blow the fuse. So first of all, let's talk about setting up the multimeter. To test our batteries, we need to check the voltage of these batteries. First of all, visual inspection will show that the batteries are not leaked, that they're intact, they look in good condition. So that's part one, visual test. Part 2, we will set this to voltage. The next thing to take note of is these connections down here. We've got 2 connections for 2 test leads. Here's our test leads. These are called probes, and we actually use these electrical prongs here, these metal prongs, to create a circuit, make a circuit with the things that we're going to test. We always try and use black for negative, red for positive. Shouldn't really matter unless we're testing diodes and polarized devices such as, well, batteries really, and capacitors. So what I will do is plug the black one in first. That's easy. It should be color coded on your meter, and that will go into the port that is labeled common. Might have a little earth sign there. Once that's in, I've got 3 choices for this. This will differ according to your multimeter, but you'll have to read your multimeter and decide which one of these go where. I could put it in the 10 amp. Well, I'm not measuring 10 amps, I'm not measuring amps, I want to measure voltage. So I'm actually going to not put it in there. The next port I've got is a separate current sensing port, which is microamps and milliamps. I could plug in there, but again I'm not measuring amps. The third port, all the way over to the right here, is actually marked capacitance, diode, hertz, voltage, ohms and degrees. So this is the port we'll want for measuring voltage. It's important that before you go probing anything with your multimeter that you've set up these connectors just right. If we actually connect to the current and we take a reading and we're not planning to get current, for example we've not got enough resistance in the circuit, we can actually damage the multimeter or damage our circuit by either short circuiting the circuit or by burning out the multimeter or blowing the fuse inside. So very, very careful that you set this up, and as a rule of thumb I always check where my cables are connected before turning on the meter to do any jobs. Can be a little bit time consuming, a little bit repetitive, but highly recommended if you want to ensure that your meter is not going to get damaged and not going to cost you money to repair. Just try and position that so we can see. I do have a light on this meter, which is quite handy. It does turn off very quickly, so it'll actually be switching itself on and off all the time. The meter also has its own power off function, which is a little bit annoying, but does ensure that when you come back to the meter, you still have battery. On some meters, they don't have auto power off, and they will run the battery out very quickly. So back to our batteries. We are going to take battery number 1. I'm going to take the red and connect it to the positive. Positive normally has the nib on the top. It also has a plus sign. So connect that to positive. Let's put light on and connect it to negative. Now, did you see I got a reading and now it's gone to 0? That's actually because I'm set to AC and I haven't got AC. I can maybe replicate AC by tapping. So I'm kind of simulating AC voltage there and I do get a reading, but it's not a true reading. So what I'll need to do is make sure that I go to DC, take my meter and measure the battery like so. We can see I've got about 1.587 volts. It's brilliant. So that battery I'd say is fairly good. The next battery we'll look at, let's take a reading. Negative to positive, 0.86 volts. So that battery is definitely at the end of its life. Now what happens if you get this the wrong way round? Nothing much. We will get a negative reading. See there, negative. Still the same number. Okay, so we know what we're looking for. So that one's dead. Let's have a look at this super high quality battery here. 1.37. So again, not bad. A little bit of life left in it. And this one is 0.308. So very much completely gone. So at the end of its life. So now I have arranged these batteries in order of how much power is left in them. Really, these two up here are unusable. This one's pretty good, and this one here is on its way out. Now, a couple of other bits of advice with batteries: don't mix and match them. When you are running batteries that are not matched or not paired from when they were new, you'll actually find that one battery will discharge into the lower battery. So this one will discharge into that battery and then you'll actually end up with 2 dead batteries. Also, the discharge can drain power so quickly from one of the batteries into the others. And let's say we went from this one with quite a lot of power to this one with very, very little. It could discharge so quickly that this battery would get hot and could actually explode. Rare case, but could happen. The other problem is if we leave dead batteries in our devices for too long, they can actually start to break down internally, build pressure up, and they will then explode and leak everywhere. So that's a way to identify whether your batteries are any good or not. Of course, the expected voltage from one of these batteries, well, they're rated at 1.5, so anything over 1.5 would suggest that they're fairly good. A brand new battery is quite a way over 1.5, nearly 1.6. Just give you that added extra power there. Of course, it depends on the type of battery as to what voltage you might be getting. And size isn't everything when it comes to batteries. So let's get a couple of batteries here and I can take a couple of readings. So, what am I looking for? I have the battery here that's labelled 2032. It's in a childproof pack and I can't actually get it out. There's the childproof pack. Come out, come out, come out. No, I don't actually know how to get it out of there. When all else fails, get some scissors on it, I reckon. How to test your battery, not how to open your battery. Okay, it also has this nice little sticker on it now that's supposed to stop children from eating it, and if they eat it, the current that actually flows from these cells can actually cause holes inside your gullet or your stomach, which is not very nice, so don't eat these. So again, we'll touch one side of the battery with one edge of the probe, pop the light on so you can see, take the battery on the other side. We've actually got 3.2 volts on this one, so this one's rated at 3 volts. So this is a good battery, brand new, straight out of the pack. And another battery that I can test is this tiny little cell down here, which is actually called a 23A. And this 23A is a nice little, let's find out, 12 volt job. So this is actually producing 12.12 volts. Now you may think 12 volts is quite a lot from such a little battery. There it is compared to the other batteries. But actually, there is no current being produced there. What we've actually got inside is a lot of little watch batteries, tiny little cells. I forget how many, but they're banked up in there, about 6 or 8 of them. And actually, if I pull that open, you will actually find it is just tiny little watch batteries. Let's see this done. So be careful. These batteries are not smaller batteries inside. And if you try and cut into them, they will explode. But let's actually have a look inside this little job, which I know for a fact is smaller batteries. I say that, I hope it is, because if not, we're about to have some alkaline or acid explosion here live. Let's just cut that off there. We can pull the bottom off. We can pull that off, and will they just slide out of there? No, they're pressed in there a little bit better than I thought. There we go. Like opening a Christmas present. And actually, if you need some small little batteries, they might be a cheaper alternative. See them there? They just tip out. And what we've actually got inside is 1, 2, 3, 4, 5, 6, 7, 8 little batteries. If I read the voltage, they are 1.5 volts each. And actually, I don't know if you'll see this in the video, but they are marked as an LR932. So if you need LR932s, and you can get hold of the 12 volt cells cheap, and the 23As, might as well just pull them apart. These, on the other hand, are a lithium type cell, and if you try and pull them apart, they will explode and possibly catch on fire, so avoid doing it with those. And the same, these batteries, the alkaline batteries, are I believe pressurized, and if you actually try and open them up, they will explode. I've seen a video on YouTube where a 12 volt battery is opened and someone tips a load of AA batteries out. Complete made up fabrication. There is no AA batteries inside a car battery. There is just a huge amount of acid. So in a car battery, you actually have, now this battery is attached to something, so I'm having trouble disconnecting it, but let's get it over anyway. This battery is what's known as an SLA battery, or a sealed lead acid battery. There it is. This battery would be more capable of starting a car. It's probably a little under power. You need quite a lot of power. And when we're talking about power, we're not talking about just volts, we're talking about amps as well. So I'm going to now connect this one up, and hopefully in the meter you can see it's reading at about 12.13 volts. So around about the same as the other 12 volt battery, but hopefully you can appreciate that if I get another one of my little 12 volters, there they are, that there is a heck of a lot more power in there than there is in there. And actually, inside one of these, thinking about the individual cells, I'm guessing there's about 20 milliamp hour in one of these, maybe a little bit more. So perfect for controlling very low power devices like a little radio fob or something like that. This one, on the other hand, in milliamp hours, has got more like 24,000 milliamp hours or 24 amp hours inside it. And a car battery may even have more, 100, 200 amp hour in it. So it's all about not just the amp hour, the number of milliamps stored in the battery, the voltage, but also its capability of supplying the current. So a lead acid battery compared to a, let's say, a lithium polymer, here's a lithium polymer, this can supply quite a lot of current compared to one of these. Fortunately, the lead plates inside the lead acid and its internal resistance means it's not really willing to give up lots of current, and if it does, it gets hot. Whereas these lithium polymers, if we measure this one's a bit over because it's a 4 cell, we're reading 14.7 volts. It tells me the stored current inside there is 1000 milliamp hours, but it also tells me it's 65C, so it can give 65 times 1000, so that can give 65 amps, which is pretty good for a small battery that size. This battery here doesn't actually specify the number of amps it can give. Probably a good amount. It doesn't specify. I'd have to do some testing. We're not going to go into testing the current capabilities of batteries, because one of the things that can happen when you're testing current capabilities is you can either blow a fuse or you can have a fire, because amps means power, power is high watts, and watts is heat. Essentially, if I create a small circuit here to measure the power from one of these batteries, I'm basically just creating a small electric heater, and if it's not managed well, it will catch on fire and blow the battery up, blow my multimeter up, or just set fire to my house. So very careful not to do that, and a way you could accidentally do that is by plugging into the 10 amp here, or even the milliamps there. And if I now actually connected to the battery, I would short circuit the battery and I would fry the circuit. So I'm just going to clear that out of the way now, and we'll come back to where we started. Just recap on that. Every time you go to check a battery, ensure that your multimeter is not in amps or milliamps, but in volts, because the last thing we want to do is short circuit the battery, over discharge the battery, damage the meter, or damage the battery. The next thing you want to do is check the voltage on your battery, and the battery should have written on it somewhere what voltage it is. So if it's 12, like this one for example, then take your probes, set on volts DC, make sure it is set to DC because batteries only provide direct current. Probe each side and check that the voltage is slightly over the voltage specified on the battery. If it is, the battery should be good. In some rare cases, the battery will display quite a high voltage and actually drop significantly when you load it. If that really is a suspicion, one thing you could do is actually test the battery in situ. So here I have a kind of antique looking flip camera. It's lost its old battery cover there. So that's perfect. What we've done here is actually turned the flip on. It is now switched on, and you will see that I can check the battery in situ while it's switched on. Hopefully. There we go, and I'm reading 1.4 volts. If I turn the flip off, it was off. If I turn it on, you'll see that the voltage has significantly dropped. 1.35, and it is dropping. I can literally see the battery running away, running out. If I turn the flip off and check it again, you can see the voltage has gone back up. So actually turning on the device uses some power, draws the voltage down. If the voltage is drawing down below the minimum, the device might stop working. Also, if the device is getting hot and running the batteries out quickly, this could signal an actual problem with the electronics itself. The next thing we're going to do is have a quick look at a plug-in power supply. So again, I do not suggest that you take off the covers off this end. We're only going to check a low voltage power supply here. So this device specifies that it will give out 5 volts at 2 amps. It's converting our 240 mains voltage into 5 volts. So I'll plug that in and we'll get to the socket end. Is this one going to be a good example? I don't know if I can get my probe up there, but we'll cover what to do in this anyway. So I'm going to get back here and plug in the power adapter. This might be useful if you're checking, possibly not phone charger because it's quite difficult to get a multimeter into a USB port, but probably things like a laptop power supply. So we're now plugged in. Can I get a probe in there? No. I can actually hear the power supply humming away, so it's not a very good one. What I'm actually going to do this check then is get hold of something that will go in the hole there. So I'm just going to get a piece of wire, small piece of wire, strip a little bit down. There we go. Connect it to one of the connectors, and that one's going to go inside, and this one's going to go on the outside. And you should see the multimeter has sprung to life. And again, we're reading slightly over, 5.18 volts. Perfect. Now, if you've got suspicion that you have a problem with your power lead, what I'd recommend you do here is try and get as good a connection up there as possible, but wiggle around in this neck point here. Very common on laptops for this point here to become intermittent. And what will actually happen is when you fold that wire one particular way, it will show a drop in voltage. But you do need to make sure you've got a good connection up here, otherwise you'll just be dropping the voltage yourself. So wiggling around here, that seems fine. Now, shouldn't really do this, shouldn't short out a power supply, but that wall supply there is telling me it's going to be 5 volts at 2 amps. And being an electronics engineer, I know that 2 volts at 5 amps is not going to cause a fire. It's not going to cause anything to go bang. And I'm actually now going to take a quick current reading off this supply. And you can see that what's actually happened here is the supply shuts down. Okay, there's some safety feature in there that causes it to shut down. If I put, is it max min? Max min, and I go select max min, I can actually take the max and minimum peak reading off here. So here we go. What I've actually done here is showing me that the maximum peak reading of current it's got out of this wall supply is 1.778 amps. Now, I would only ever recommend doing this on a current limited supply, i.e. a power supply that transforms power down to a low current, low voltage, no more than 2 or 3 amps. Anything more than that, we actually risk overheating the multimeter, overheating the power supply, or possibly damaging the power supply. And you hopefully noticed that when I did this test, I very quickly just pulsed that in there, very quickly. If I held it there, everything's going to get hot. And there'll be lots of engineers out there saying you shouldn't be doing that with your power supply. But to me, for quick testing, it has proven that this supply is giving me about 5 point something volts, and that I can get about 1.77 amps out, which is not the peak. But don't forget, I can hear the power supply is shutting down. It's actually a switch mode power supply, and it's saying that this is a bad situation. I've detected a short circuit, so it throttles the current back. Later, we'll use power resistor to actually simulate a load on the power supplies, and we can stress test them. You'll need something like this big old rheostat big old resistor, and like I said, we're essentially making an electric heater here. This acts like a big old electric heater that can vary the amount of power it takes. Shouldn't get hot, but it can take getting hot without burning out. We'll look at that next.